Inductance. A current generated in a conductor by a changing magnetic field is proportional to the rate of change of the magnetic field. This effect is called inductance and is given the symbol L. The effect of an inductor inducing an EMF into itself is called self-induction, but often referred to simply as induction. When an inductor induces an EMF into a separate nearby inductor, this is called mutual induction and is a property used by transformers. The changing magnetic field created around a conductor by the changing current in the conductor causes a varying EMF to be set up across that conductor. This varying EMF in turn produces a varying current flowing in the opposite direction to the original current. The changes in this current therefore oppose the changes in the original current. If the original current is increasing, the induced current will slow the rate of increase. Similarly, if the original current is decreasing, the induced current will slow the rate of decrease. The overall result of this is to decrease the amplitude of the AC current through the inductor and so also reduce the amplitude of the AC voltage across the inductor. Inductance. It is measured in units called the Henry H, named after the American physicist Joseph Henry, 1797 to 1878. 1 Henry is the amount of inductance required to produce an EMF of 1 volt in a conductor when the current in the conductor changes at the rate of 1 ampere per second. The Henry is a rather large unit for use in electronics, with the millihenry mH and microhenry μH being more common. These units describe 1,000th and 1,000,000th of a Henry respectively. Mutual inductance. When an EMF is produced in a coil because of the change in current in a coupled coil, the effect is called mutual inductance. The EMF is described by Faraday's law and its direction is always opposed the change in the magnetic field produced in it by the coupled coil. The induced EMF in coil 1 is due to self-inductance L. The induced EMF in coil 2 caused by the change in current I1 can be expressed as EMF2 is equal to minus N2 delta phi by delta T. EMF2 is equal to minus M delta I1 by delta T. M is equal to minus EMF2 upon delta I1 upon delta T. If delta I1 upon delta T is equal to 1, then M is equal to EMF2. Z coefficient of mutual inductance of two coils is equal to the numerical value of the induced EMF in one coil when the rate of change of current in the other coil is unity. The most common application of mutual inductance is the transformer.